All right, so this is a continuation of presentation from yesterday. So yesterday, just to remind everybody, we talked about basics of CompuCell 3D. I showed you how CompuCell does computations under the hood, what happens at every pixel copy, what happens in between Monte Carlo steps that we call steppables. And then we played with simple simulations. The first simulation was we used contact energy only, and we played with positive or negative contact energies. And if you remember, if we use negative contact energies, the cell occupied entire lattice, because that was the best way to minimize energy by increasing number of interfaces with negative energy. And if we used positive energy, cell disappeared, right? Then we added a volume constraint to control shape of the cell, and then we ended up our presentation with this cell growth model. Okay, so let's actually jump right into the model again. I'm gonna go ahead and open this in CompuCell. If you noticed, I prefer to use terminal when running CompuCell. And the reason I prefer using terminal as opposed to shortcuts is, you know, occasionally if you get an error from CompuCell and if CompuCell crashes, then the console that pops up with the CompuCell will disappear. But if you start CompuCell from terminal, just like I do here, and even if there's an error, the terminal will stay open, and then you can essentially send us a feedback. You can say, hey, look, you know, I ran this simulation and this is the error. So that helps us with debugging. All right. So let me open up the simulation from last day workshop. And then we're looking for cell growth. Okay, let me hit open. Let me move this to the center of the screen. All right, and soon we should see a single cell that just keeps growing. Okay. So there is nothing really fancy going on in this simulation. Cell keeps growing. The way we achieve cell growth, and let me switch to presenter mode. I'm just going to get rid of this. The way we achieve cell growth is essentially in step function that is called every single Monte Carlo step, we iterate over cells. And then if the cell type is of type tumor proliferating, we increase target volume by 0.2. I want to maybe take 1 minute and explain this syntax here, self.tumor proliferating. I'm not sure if somebody explained to you, but essentially each cell type in CompuCell has type ID associated with it. So medium traditionally has type ID 0, and then you define additional types. So we have tumor proliferating, and necrotic, and they have type IDs 1, 2, and 3. So what you could do here in the syntax, you could type if cell type in 2, right? Because type ID of tumor proliferating is 2, right? Or you can literally take this type name, capitalize all the letters, and prepend self dot to that. So you have self.tumor proliferating, all copies. And this gets resolved in CompuCell as type ID 2. So this is a convenient way to essentially put more meaningful code in your scripts, right? So instead of actually typing number 2 and looking up what number 2, what type number 2 corresponds to, you can just use this syntax. All right, so that's the simulation. So nothing fancy going on. So now let's see what we can do to take the simulation to the next level. So let's learn how to divide cells. Okay, so before I start talking about how to divide cells, let's look at this picture here. So this is the cell from the simulation that we will run soon. So the simulation is called Cell Growth 2. So you can get it from the students folder. And just to remind you, the folder I think that all those simulations are stored in is called CC3D_theory. So before the mitosis, we have just one cell. Okay, now if the cell grows and it reaches a doubling volume, and doubling volume doesn't have to be, strictly speaking, doubling. I mean, you can have arbitrary condition on when the cell divides, but for simplicity, let's assume that we're talking about doubling volume. So let's assume that this cell is already at the doubling volume. So then we're dividing this cell, okay? And what happens is that in the process of the division, CompuCell will create a new cell object, and this object of the cell that gets created will be referred to self.child cell. Okay, so this is how you will refer to that object in Steppable. The object of the cell that existed before mitosis is referred to as self-parent cell. Okay, so I want to emphasize this, that in biology we essentially are talking about daughter cells, two daughter cells after that are after division, right? But in order to keep track of objects that represent cells, we introduce this terminology. One is referred to self-parent cell, the one that existed before mitosis, and the other one is self.child cell. All right, so that's a little bit of introduction. So let's look at how we would implement this mitosis Steppable. So maybe let me jump to 2 slides ahead and explain what's really going on here. Okay, so mitosis Steppable is just like any other Steppable, except it inherits from mitosis Steppable base, right? So there are some different functionalities coded up in this mitosis Steppable base, which I'm not going to talk about. But it's sufficient to say that if you want to implement mitosis Steppable, you have to inherit from this base class. Okay, in the step function, first thing that I'm doing, I'm constructing empty list of cells to divide. So this list will hold cells that I want to divide in this current Monte Carlo step. Okay. Next, I'm iterating over all cells, and I'm checking if cell volume is greater than 50. And I want to emphasize that this condition here is arbitrary. I know that my target volume for this simulation for cells is 25. So doubling volume is 50. But you can easily extend or modify this condition to adapt to your needs. And we will do this exercise in a second. But anyway, I'm checking if the cell volume is greater than 50. If it is, I'm going to append this cell to the list of cells to divide. Okay, so this is my first loop. Then I'm going to do second loop. And in the second loop, I'm looping over cells to divide, right? And then for each cell that is in this list, ready to be divided, I call self-divide cell random orientation, okay? That means, what does it mean? That means that I'm taking the cell and I'm randomly choosing the orientation of the cleavage plane, right? So in this case, I was dividing along this cleavage plane. But, if you run this function again, the cleavage plane might be oriented differently, will be oriented differently probably. It's very unlikely that you will get 2 divisions along the same plane in a row. Okay, so that's the code. Now, the reason why mitosis Steppable is special is because immediately after you call this divide cell random orientation function, a function called update attributes gets called, okay? So you're doing single division here, okay? So you have, let's say you have 100 cells to divide, but you just picked cell number 3, and you're trying to divide this cell, right? And after the division of cell number 3 takes place, this update attributes function gets called. So why do we have this update attributes function? Well, because when CompuCell creates cell, new cell, this cell does not get initialized. I mean, it doesn't inherit properties of the parent cell. So in other words, this is a cell object that has type ID 0, which means it's not, we have to change this type ID. Target volume is 0, lambda volume is 0, and so on, right? So we want to make sure that you have an opportunity to initialize the properties of the child cell to whatever you need. And this is what you do precisely in the update attributes function. So first thing that we do in update attributes function, we lower target volume of the parent cell by 2. Why do we do this? Well, because, if parent cell has volume 50 before the division, right? Then after the division, this cell has volume, roughly speaking, 25 pixels, right? Now, if I leave target volume at 50 or more, as it was before the division, then this parent cell will essentially explode, right? And we don't want it, because parent cell will try to adjust its volume to the target volume as quickly as possible. We don't want it. We essentially say that, okay, since we are dividing cell into 2 pieces, we have to adjust target volume accordingly. So that's why we are dividing target volume by 2. And next, we are calling this convenience function. That's actually quite convenient because, in early version of CompuCells, we didn't have this function, and we had to initialize all cell properties by hand. So what this function does, it clones properties of the parent cell to child cell, okay? So in other words, whatever properties parent cell has, after calling this function, child cell will also have the same properties. So that means, type, lambda volume, target volume, and so on. But then we are adding another twist here, essentially, and we are doing type differentiation. So if parent cell is of type tumor proliferating, then the child cell will be of type tumor, okay? And if it's not, then the child cell will be of tumor proliferating. So essentially the idea here is that we want to end up with a checkerboard. So we want to create cells of tumor or tumor proliferating, depending on the type of parent cell, okay? And if we go back, a few slides back here, if you add this mitosis steppable, you have to register it. You have to, in the main Python script, you have to import this mitosis steppable and register it, right? So that's the only thing. And this class cell growth steppable is exactly the same as it was before. So so the only new thing really is this mitosis steppable that we went over. So let me actually switch back and get the presentation. Sorry, let me download. So I'm downloading cell growth tool. Let me open it, actually save it. And then I'm gonna go to CompuCell and stop this current simulation. And I'm gonna open cell growth to zip. Okay. Let me reset the view. So this is our single cell, okay, that I created after first Monte Carlo step. Okay, so already a few pixel copy attempts took place. So my cell is no longer squarish. Let me reset the view and let's run it. All right, so you can see that already we had several mitosis events, right? And the idea was, and I will zoom in a second, and the idea was that if we go back to the presentation, let's go back here. So the idea was that we were supposed to be getting, different types of cells, right? So if cell is proliferating, tumor proliferating, the child cell should be tumor, and if it's not, then the child cell should be tumor proliferating. So I should expect that I should have more than one green cell, but all I have are blue cells. And the question to you is, if you look at the code, and let me open this into edit. If you look at the code, can you tell, or can you spot the line, or can you modify the code that is responsible for actually creating cells of only tumor proliferating or only blue cells? So let me open up to edit. I'm gonna go open new terminal. CC3D. So let me open up this. All right, so why do you think we are getting only, why all cell types, the child cells, are of type tumor? Or why do we get blue cells as a result of the division? So let's take a few minutes, maybe not a few minutes, maybe a minute. Let's look at this code and see if you can spot the place that is responsible for the situation and how you would fix this. All right, so in the interest of time, because we have lots of material to cover, I'll tell you this right away. So the reason why all our cells that we are producing as a result of mitosis are blue or of type tumor is because of this line here. And to be honest with you, when I actually was writing this, preparing this simulation, I was also puzzled why I have this behavior, and I thought that would be a good question to ask you, this little brain teaser. So I'm actually close this. So what happens is this: the only cell in the simulation that grows is of type tumor proliferating. So this is this green cell, right? If this is the only cell that grows, that means this is the only cell that divides, right? So there's no way that we ever will get blue cell dividing here, right? And this is why we are getting the only cells we're producing are of type tumor or blue cells. So if indeed that's true, let me actually comment out this code. And I have to do a little adjustment here. Save the simulation. And let's run it again. I'm gonna switch to CompuCell. I'm gonna stop the simulation. And now we should see a slightly different picture, right? So this was the simple exercise, simple tweak that we can do in the code to essentially achieve different patterning here, right? And it was somewhat unintuitive to look for the cause of this behavior in the other steppables. Maybe it shows you the fact that actually when you're running steppables, it's actually important to be aware that they are not completely independent of each other, that one steppable can influence outcomes of the other steppable. And the other thing, and we will get to this in a second, is the order in which steppables are called, okay? So let me actually go back to this main Python script. In this section, you can import steppables in any order you wish. It doesn't matter. But what matters is the order in which you call those two lines, or you code those two lines, right? So the steppables are called in the same order they are registered. So for example, in this situation, cell growth steppable will be called before mitosis steppable. And this will be actually quite important in the next section, where we will do some plotting. All right, so that concludes the mitosis. So hopefully this material is clear. We'll revisit, of course, mitosis a few other times in the subsequent tutorials. All right, so let me switch to presenter mode. Okay, so now let's modify this simulation, the previous simulation, and include contact inhibition of proliferation, or actually contact inhibition of growth, which will in turn turn into contact inhibition of proliferation. And maybe I shouldn't be calling it contact inhibition, I should call it like pressure-dependent growth rate. Because what we will do here, we will take our old cell growth steppable, and if you remember, previously we will just increasing target volume but by 0.2. But this time, what we will do, and the simulation is contact inhibition of proliferation, and it's in the students folder. So this time, what we will do, we will compute the increase in target volume, which will be defined as a maximum value between 0 and this expression. And I'll explain what that is. So let's look at this term here. So we can define pressure, internal pressure of a cell, as a difference between, should actually double difference, but let's, for simplicity, let's talk about this simple metric. So the pressure inside the cell can be defined as the difference between target volume and actual volume. And why do we define it like that? Just to get intuitive feel, is imagine that your target volume is 100, but the cell volume is 10. So that means that target volume is 100, but you have tiny cell. That means that this cell is under tremendous pressure, right? So that's why, intuitively you can see that this expression as a metric, as a measure of cell pressure makes sense, okay? And what we want to do, we want to make sure that as the pressure, the cells that are more compressed, they grow slowly, right? So we are taking our base rate of 0.2 pixels per Monte Carlo step, and we are lowering this rate depending on how big the pressure is. And then there is proportionality coefficient here, 0.05. okay? So this is my expression of delta. Now, the reason why I'm using max function here is because you can imagine that it can happen that the pressure is so big that the delta, the increase in target volume, could turn negative, right? And if you don't want negative growth or cell shrinkage, what you could do, you could essentially put this max function, and it's a, you know, simplified way. I mean, you can come up with, you know, more analytic method, right, that avoids discontinuity. No, not discontinuity, but avoids, make sure that first derivative of the delta expression is continuous, right? Max function has this sharp, may have the lead to, you know, piecewise, to the function that whose first derivative is not continuous, but you get the idea, right? So the reason why I have this max function is essentially we never let delta to be less than 0, okay? And this is the simulation. Now, in addition to that, in addition to implementing this contact inhibition of proliferation, I want to see the effect that this contact inhibition of proliferation has. So in other words, let me maybe switch back to this view. So in other words, if I have contact inhibition of proliferation, that means that I'm expecting that cells in the middle are compressed and cells at the outskirts of the blob are less compressed. So that means that cells at the periphery of the blob should be dividing faster, right? And cells in the middle should be dividing slower. But how do I visualize this, right? So one way to visualize this is to create additional view where each cell before the mitosis will be colored, just before the mitosis takes place, will be colored using, essentially using different color, right? So if we go back to the presentation here, what we are going to do, we will create additional scalar field. So this is a visualization that we can use in CompuCell. And the way you create it is by using self-create scalar field cell level py, right? And again, if you don't know this function, I'll show you where to put this, where to find it in Tweedit. It's one of those CC3D Python helpers. And what we will do in this function, we will iterate over a list of cells, and if the cell volume is greater than 50, we will assign scalar 100 to this all the pixels that represent the cell on the lattice. And if it's less than 50, that is cell that is not ready to divide, all the pixels that belong to that cell will have a value of 1. And then we will plot a color. And the important thing here is that we want to register this mitosis ready plotter steppable before mitosis. And the reason is hopefully obvious, but the reason is that we want to catch any cell that has cell volume of greater than 50 before mitosis takes place. If we switch the order, we would see nothing, because after mitosis takes place, all the cells by definition will have volume less than 50, right? So that's the reason why I mentioned before the order in which you call steppables matters. So let me go to, and you can do the same. Let's go to CC3D theory, and let's grab this contact inhibition of proliferation, and let's run it. So I'm going to download it. Okay, we're ready. We'll stop this simulation and I will open contact inhibition of proliferation. Okay, and let's run it. Okay, so let me actually pause for a second. Let me move this. So we have two fields. We have cell field and this mitosis ready cells. Okay, so let me reset the view. So essentially, if you look at this picture here, at the bottom of the screen, there's annotation that displays what is the minimum, and maximum value of the field. So the maximum value of the field is 1. That means that this cell is not ready for mitosis. So in other words, the cell volume of this cell, the volume of this cell is less than 50, right? If we keep running that, oh, and one thing I have to mention right now, if you noticed, my Monte Carlo steps here, I'm essentially plotting every single Monte Carlo step. That's quite inefficient, and this will slow down the simulation. So I'm going to go to configuration, and I'm going to change update screen frequency to 100. Okay, and you can do the same. So the trick with this simulation is to let the blob increase its size so that we have, you know, decent sized blob, and then switch to screen update of every Monte Carlo step. And I'll explain why in a second. So things take place. So now the reason why you may ask me why I'm not seeing anything, why I'm not seeing those cells that are ready to divide, and clearly some divisions already took place, why I'm not seeing any marks here. Well, you're not seeing that because remember, we are plotting, we're displaying snapshots every 100 Monte Carlo steps. So cells can actually, don't wait to every 100 Monte Carlo steps. They divide stochastically whenever they reach the volume. And it happens so that it's quite uncommon to see cell division take place at exactly Monte Carlo steps that's divisible by 100. But you can see that some divisions took actually place because the scale here on the left-hand side jumped to 100, right? So there was an event, we just missed it. And I will run for a few more seconds, and then I will switch to screen refresh, and let me actually do it right now. Screen refresh every single Monte Carlo step. So I'm going to go back, change screen update to take place every single Monte Carlo step, and I'm going to run it. Hopefully, we'll be able to see some. So you can see some red dots popping up occasionally, and you can see. And if we keep running the simulation, you can see that that most of the divisions actually take place outside or close to the boundary of the blob. So indeed, cells in the middle seem to be compressed. They will not divide. They will divide at a much slower rate. And again, it all depends on the settings of your simulation. So let's run for a few more minutes, and then I think we'll move to our next exercise. So I just want to mention another way, maybe more quantitative way of actually plotting the data about cell division. You can, what you could do You could measure, for example, center of mass of the blob. You can write a function that measures center of mass of the blob. And then each time the division takes place, you can log this event in a file, and you can output the text file. And after the simulation is done, you can analyze. And then you could essentially create, I don't know, a histogram of you know, how many division took place as a function of distance from the center of blob. You know, you can be quite creative here. And actually, when we talk about parameter scan later today, I'm going to show you one of the exercises and how you can use CompuSol to output data files that later on you concatenate and analyze and post-process. And some of the simulations that we are doing, especially those that involve multiple replicas of the simulation, are done this way. So you run multiple simulation, you log the output, you concatenate the output, and then you analyze the results. Actually, you can learn a lot by performing those type of analysis. You can get really quite creative. All right, so let me stop this here. Hopefully, you could see that indeed this contact inhibition of growth and thus proliferation seems to be working. And again, keyword is seems, I mean, because we haven't done any quantitative analysis, but qualitatively you see that the cells at the outskirts or the periphery of the blob tend to proliferate more, which is to be expected. All right, so let's jump back to the presentation and let's see what the next topic is. Oh, I forgot to mention one thing. How would I add? So this is my old cell growth field. So cell growth step. How can I add new? How can I add new steppable? So what I did really, you know, if you want to add steppable to CompuSol 3D steppable file, go to this left-hand panel, you select steppable file, right? So we have main Python script, XML script, and steppable. Right-click, okay? And you click Add Steppable. And then I think it was called Mitosis Ready Plotter. You hit OK. And then your new template for new steppable gets pasted in. The step gets registered. And what you can do, you can move this import to the upper section. And then I think we were talking about rearranging the order of making sure that Mitosis Ready Plotter gets called before Mitosis Steppable. Then here we have to add this cell field, this scalar field. So I'm going to CC3D Python, extra fields, and scalar field cell level. So scalar field cell level has to be, it tells me it has to be initialized in init function. So I want to make sure that I'm inside init function. This, and I think we call it Mitosis Ready Steppable. I don't think we're doing anything in start function, so it's safe to delete. I'm going to delete those two other functions because we're not using them, so just to save space. And inside here, first thing I'm going to do, I'm going to clear this field. So again, extra field, There are a few things. I'm sorry. I shouldn't be calling field steppable. I should call it mitosis ready. Mitosis ready. So in general, in CompuCell, when you want to access any field, whether this is cell field, whether this is chemical field or additional visualization field that you created, you just use self.field. And you just literally copy and paste name of the field, okay? And then I think what I want to type here is, sorry, if cell dot volume greater than 50, I want to set 100 field. So this is exactly what I did when I was preparing the presentation. I used CC3D Python, and that's how I wrote this stuff. And I'm not going to run this because it's exactly the same simulation as we did before. So let's, the other thing, you know, when CompuCell pastes those templates, those imports end up being pasted in the middle of the file. It's not really proper Python. It's correct, this code will run, so there's nothing wrong here, except that from stylistic standpoint, it is best to move all those imports to the top of the file, so that if somebody else reads this file, they can see from the very top of the file what modules are imported. And clearly this line gets duplicated, so I'm gonna get rid of it. Let me save it. And let's move on to the next section. Okay, so the next section, we'll talk about, we'll talk about, so this is essentially an instruction to switch to screen update frequency once we have enough cells. We covered that already. And let's move to the section where we put everything together. So this is final exercise. Well, actually, not really. We'll talk about one more sophisticated model, but this is the exercise that we'll do together. And I will explain in detail the code for this part. So we'll do a vascular tumor simulation. So far we have learned how to use contact energy and volume constraints to control the cell shape. We know how to grow cells, we know how to divide cells. You know how to add diffusive field. I'm not gonna talk through that because I think TJ covered it. TJ and Josh and Giuliano and James probably covered it earlier. We know how to change the cell type, right? That's easy. So now we can combine those techniques and build a simulation, a simple simulation of a vascular tumor. So the idea is simple, right? So you start with a single cell, the cell grows, as we have seen, but then, oh, and the other thing that I forgot to mention, the cell grows, and the cell grows in response to nutrient level. So nutrients are supplied by medium. So all this space around cell field supplies medium at a constant rate, okay? So for example, in this situation that we have on the screen here, since this part of the lattice is occupied by cells, the nutrients are being supplied only from the outside, and those nutrients diffuse, right? So they have to diffuse and essentially provide nutrients to the cell growth, right? So if the cell experiences a high level of nutrients, it grows very fast. If the nutrient level drops below some critical value, then cell stops growing and turns necrotic. So it's really simple model, right? And once cells turn necrotic, it doesn't turn back. right? So it just stays necrotic. And this is the outcome of the simulation. Okay. So perhaps let me go to the next slide. Maybe let's talk a little bit about the code. So what I'm going to build a vascular tumor steppable, right? So in start function, I'm creating a single cell of type tumor proliferate. So we have already seen this code. Okay. In the next section, the step function, what I'm doing, I'm getting a reference to the field nutrient. Okay. A nutrient field is defined to be a diffusive field. In the for loop, there is a first for loop. I'm going through list of cells and I'm computing rounded to the nearest integer center of mass of each cell. Okay. And I'm using this convenience function that takes argument that is of type float. So x is of type float. It rounds it to nearest integer, and then it casts it to integer type. Okay. So I get this. And then I'm checking the nutrient level at the center of mass of a cell. Right? So essentially, I'm computing center of mass of a cell, and I'm checking what is my level of nutrients. Okay? And then my growth is a combination of two components. So there is nutrient-based growth component, okay? That is, so the minimum value of nutrient growth-based component is 0.2, but then if my nutrient level is higher than 0.2, I have to walk it back. So that's right. So if my nutrient level is low, so that 0.01 times nutrient level is less than 0.2, my growth rate is this expression, and the growth, nutrient-based growth component is capped at 0.2. So I don't want my cells to grow too fast. Even though nutrient level is super high, I don't want them to grow very fast. And of course, you can, instead of using min function, you can use Michaelis-Menten type of expression. It would be probably better, but I wanted to keep the code simple. That's why I used this min function. So again, and then there is another component that is our old friend, pressure dependent growth, right? So we use the same expression as we used in the last simulation. And again, we want to make sure that growth is never negative, right? So that's why we're using this max function, right? And we increase target volume. Now, sorry, let me go back here. The interesting part is here, and what happens here at the bottom of the screen is, interestingly, this is truncated. So actually, let me, so if my number of cells in my simulation is greater than 200, I will have a condition that checks for the nutrient level, and if the nutrient level goes below 20, my cell turns necrotic. And unfortunately, this code is truncated. So let me actually go back to the excuse me. Let me go back to my simulation file, and let me grab this vascularized tumor and open it, download. And I'm going to open it into Edit and actually explain things into Edit. Might be easier. Close this. And a vascular tumor. Click. Okay. So this is the code that got truncated. So if my tumor, a vascular tumor, has more than 200 cells, I'll use this condition that if nutrient level at the center of mass of any cell is less than 20, I'm turning this cell to be necrotic. Okay, and then the cell stops growing and dividing, right? So essentially, if you look at if I get rid of those printout statements, so essentially in, I don't know, 70 lines of code or so, you can code not so trivial simulation, okay? There is a little bit of cheating. For example, I had to, I coded up here, arbitrarily chosen number of 200. When I'm turning cells necrotic, I could be more fancy about that condition and not put arbitrary condition like number of cells. I could also use better better functions that control cell growth instead of using min and max. But essentially, the simulation captures essential components of the avascular tumor growth. If we look at the XML, again, nothing surprising, nothing fancy. I'm just using simple diffusion solver, and I'm creating this field nutrient. So I forgot to mention that we were looking at the Python code here, and we saw, hey, I'm trying to fetch field nutrient. Where does the field nutrient come from? Well, it comes from this diffusion solver. So in this diffusion solver, we have a nutrient field, and as you can see, secretion takes place only in medium at the constant rate. The global diffusion constant is 0.05. The decay constant is 10 to the minus 3. And that's essentially it. That's all the simulation. So if I run it, I should go here and open this vascular tumor. So here I'm plotting nutrient field, and this is my cell field. So cells keep dividing, and let's run this simulation for a few more seconds. And then after we are done with that simulation, we're gonna switch. Okay, so the tumor gets bigger. Notice that the level of nutrients drops. We're still quite far from the, yes, now we've reached this magic threshold of 20, so the minimum value is 20. And you can see that necrotic core forms. Okay, so it's a simple simulation. It's not. I'm not using biological parameters. Perhaps the growth is too fast, but it gives you an idea of what it takes to build a simulation like that. And then you can see that you have this viable rim outside, so only cells at the periphery of the blob actually grow and proliferate. And since there is this pressure inhibited growth, most of the growth occurs at the most outer layers of the blob. And that's the simulation. So if we were to recap this whole session that I presented yesterday and today, so you could see that really 6 or 7 exercises, and relatively simple exercises, you must admit. I took you from a simulation that had single cell to simulation where you can build a vascular tumor fairly easily. And that's sort of like a testament to the fact that, you know, if you were to code all of that by yourself, you would have to spend way more time than we have spent building this simulation, especially that we have helpers like, you know, those CC3D Python helpers, which are actually quite handy, and hopefully TJ showed you before that you have also this XML helper. So if I want to add, let's say, I don't know, what do I want to add? Kernel diffusion solver, perhaps. I could use this simple trick to input paste in the code for kernel diffusion solver. So this is just a side note. Let me undo this. All right, so this brings us to the final part of my presentation, and this one will move much quicker. But doesn't turn out. All right, so we went through those exercises. Now the question is, how much work do you think it would take to go from our simple avascular tumor to a simulation that looks like that? So this is a simulation that Abbas has built in 2009. So this simulation was actually done with a custom version of CompuCell, and recently we have actually added the code for this simulation to our demo repository that's included with every CompuCell distribution. So if I were to ask you, like, how much work do you think it took to actually build this simulation? Do you think it was much more work or less work, or like comparable amount of work? Well, surprisingly, the answer is, and it was also surprising to me because I ported this simulation to the latest CompuCell recently. I was really surprised how little coding it took to actually build this simulation. Right? It looks complex, it looks fancy, and I'll show you the code, and I'll show you the movies, and we'll run the simulation together. But it's sufficient to say that really this entire simulation, the main script for the simulation, is in all entirety presented here. So we have, how many steppables do we have? 1, 2 steppables. We have mitosis and volume parameter steppable. That's it. So 2 steppables, just like with avascular tumor, right? So before we run this simulation, let me actually go back and maybe show you how to, I want to go to workshop. So this is the movie from the simulation. So what we see here, we see tumor growing in 3D. We have vascular structure, and the vasculature supplies nutrients, right? And the cells consume nutrients, and they grow in response to the level of nutrients, just like we did this in our simple avascular tumor, right? The nice thing here, so in this particular instance of the simulation, the vascular network also evolves. So cells in the tumor cells, when they are hypoxic, they secrete VEGF signaling. They secrete VEGF signal diffusing field, and as a result, the VEGF signaling the vascular structure gets extended and penetrates the tumor. And probably, well, let me actually show. No, that's the wrong simulation. That's the other type of simulation. So let me actually open this one. So vascular, so let's start over. So the cells inside the tumor, they are hypoxic, they are deprived of nutrients, they say send vascular signaling, and you can see those purple vessels are the new vessels that are created in response to VEGF signaling, and they actually penetrate the tumor and they deliver nutrients to the tumor. So you can see the tumor gets vascularized and it grows. Right? And the more nutrients the tumor gets delivered, the faster it grows. And at some point, it will occupy the entire eyes. Okay, so that's the simulation number one. And then we use this model to essentially ask different questions. What would happen if somehow we were able to block the VEGF signaling? So what would happen if you could actually prevent those new vessels from being created? So let me run this simulation that I ran before. This is what happens. So now, this time we are not creating new vessels. And observe what happens with the tumor. So tumor this time does not grow as fast, but interestingly, in order to get nutrients, the tumor aligns itself along the vessels so that it can get somehow nutrients. So in a sense, suppressing the vessels produces more migratory, more, I don't want to say metastatic, but let's use this metastatic tumor. The tumor that in order to survive does whatever it takes to get nutrients, and this whatever it takes in this case happens to be, hey, I'm gonna migrate and align myself along the blood vessels. So this is the simulation. So let's go back to the presentation and let's look over code highlights, okay? So I don't know why this got, anyway. This table essentially lists different types of cells that we have in our simulation. So we have cells, normal tumor, hypoxic, necrotic, and vascular cells. And, you know, hypoxic cells consume nutrients. They also send VEGF signals. Not hypoxic. Tumor cells consume nutrients. Hypoxic cells send VEGF signaling, and active vascular and inactive neovascular, they react to VEGF signaling by either growing or not growing or proliferating and so on. So essentially the idea is that like if neovascular cells see high level of VEGF signaling, they respond by growing. And proliferating and extending itself so that they can deliver nutrients to tumor. So this is the XML. I'm not gonna go through every single field of the XML, every single line. There are dots here. So I just wanted to show you what type of plugins we used. We used neighbor tracker because we want to control essentially the growth of vascular cells, and we'll go over that, how that happens. We used chemotaxis, cells chemotaxed to essentially deliver nutrients. We have center of mass, contact energy. Well, we have several cells, so I had to truncate this specification of contact energy. We have growth, so we need volume constraint. We have surface to measure surface. We have focal point plasticity. So focal point plasticity, and I think we'll talk more about it, is a way to link center of masses of cells so that certain cells always stay together. And we use this focal point plasticity to essentially constrain vascular structure, I think. And then we have initializer. So there's PIF initializer that we use to initialize initial layout of cells, and we use diffusion solvers. And that's the entire XML. If you look at the Python code, so this is this main stepable. It's in its all entirety, I believe. Well, I don't have start function, but the bulk of the simulation is coded up in this stepable. So you can literally go through the code and see what the simulation is doing. So for example, if I were to go through the code and see what happens here. So it says if cell type equals 6. So this is neovascular cell. I'm computing center of mass on this cell, just like we did with a vascular tumor. Then I'm checking the concentration at the center of mass of neovascular cell. And if the concentration is greater than 0.5, here we have a threshold, then I will walk over cell neighbors, right? And I'm gonna compute total contact area of this cell with neighbors. And if this total contact area is less than 70, my cell will grow, will increase target volume and surface, target surface, right? So essentially here we are implementing this contact inhibition of growth, right? And this time, instead of actually looking at cell pressure, we're looking at, hey, how many neighbors I have around me? If I have too many neighbors, I'm not growing. If I have fewer neighbors, that means my total area of with neighbors is less than 70, I'm growing. And we do the same for one cell type. We do exactly the same algorithm for another type, right? And then here we are going to tumor cells. So this part covers vascular cells. And here we are handling tumor cells. And again, if we're looking at the concentration at the center of mass of malignant or normal tumor cells, and I remind you, why do I call it normal? Because my cell types, where is it? Normal. The proliferating cells are called normal in this simulation. That's why it's called normal. I refer to it as normal. So we check the concentration, and if the concentration is between nutrient thresholds, we can do cell differentiation. If the concentration falls below a certain level, and again we have this condition: if Monte Carlo step is greater than 100, right? So we wait a few Monte Carlo steps before we actually start cell differentiation. So it's very much similar like we had in our avascular tumor simulation. And then, of course, we also control growth rate that is dependent on the concentration. And we are using here this Michaelis-Menten type of expression that I didn't use. I used mean and max, but you get the idea. It's similar thing. And yeah, that's essentially the entire simulation. So if I were to run this simulation, let me actually get out of this. So this is my last slide for this section. Let's get out of this presentation and let's grab this vascularized tumor model. I'm gonna save it. I'm gonna open it up. CompuCell. Stop this. Okay, it's stopped. Workshop and vascularized tumor model. Okay. So this simulation will take a while to run. It's not a simple simulation. So, so you can see it already started running, hopefully. Or maybe it is during initialization stage. Let me check. It takes a while to initialize the simulation. Keep in mind, this simulation is, oh, it is running actually. You can see it here. We are in Monte Carlo step 3. So let me come here. Let me stop. simulation, and so I pause the simulation. I'm gonna go to 3D view. And again, it takes a while to, to render the simulation, but you can see that we have this initial view. So this is the initial configuration that we start with. Somewhere in the middle, there must be a cell that's growing. I think you can see it here. There's a little bluish speck here. So there is a cell. It will start growing. And if you're patient enough, and by patient enough, I mean, if you wait a few hours, you will, at the end of the day, you should see your simulation being displayed. I mean, you can see the progression. One thing to be aware of is if you're doing this 3D visualization, you know, this is slow process essentially to render the field in 3D. So to deal with that, you usually want to refresh your screen every 100 Monte Carlo steps or so, or switch to the 2D view and essentially have simulation advanced 1000 Monte Carlo steps and then look in 3D. Turns out at the end of the day, if I were to stop this simulation, I'm gonna stop it now. If you wanna stop the simulation, at the end, the computer produces this performance report, and it essentially tells you where you spent most of your time. Okay, so it turns out that this simulation actually spends most of the time running C++ code. If you see that your Python steppable takes too long, it's a good indication to actually consider rewriting the simulation in C++, the steppables in C++. And yeah, this other time is either initialization or plotting. Okay, so so you can see that visualization can be actually quite time consuming, especially if you have a lot of cells. So I think that's it for this section. I'll turn.
Maciek, why don't you make sure everyone can upload it and run it before you end? And maybe show also 3D visualization of that layout, right?
Oh, 3D visualization of layout, hold on.
But they haven't seen it in 3D. So I would make sure everybody can upload it and run it. I've done a poll and about half the people have been able to do it so far. I think it's important so that people will be able to get this before you break.
So let's do it again. So while the simulation keeps running in the background, let it run for a few seconds. So you go to the student materials, and then I think it's called Maciek class. Let's see. Yes, you go to Maciek class, and then you get vascularized 3D tumor. I right-click, I download it here, and you download it here. Now, let's actually open this simulation into Edit. So if you don't have latest version of CompuCell, you would use vascularized. You would open it first into Edit, the zip file. What happened? File crash. It's really interesting. I know what I did wrong. So the reason, so this is interesting. So I tried to open this zip file as a text file. I used the wrong file open. So you can either do open CC3D project, or you can do file open. And I mistakenly picked file open. This is one thing that I need to fix. read it. Let me go back here. Let's make sure that this is right. Okay. Create a folder. Okay. So the entire code of the simulation takes the Python code, Python step book. It's 170 lines, give it or take. And again, I just want to emphasize, it's not that much different from what we have done so far. Of course, it took a little bit of parameter tweaking and careful studies and many runs, but you would have to do it, you know, regardless what type of program, what type of software you choose, you would essentially be doing the same. So XML is not too complicated either. As usual, the most complex part is specifying contact energy. We have focal point plasticity, which I'm not going to talk about right now. This will be covered later. Flexible diffusion solver. We use this for VEGF signaling. And then we have oxygen. So we're using a special type of solver called kernel diffusion solver. It essentially is a solver that is good at handling diffusion constants that are large. And to be fair, actually, I think if we break down the runtime of each module, I would probably guess that most of the time in this simulation is being spent actually solving diffusion equations. So POTS section or the pixel copies do not take as much time. The most time is actually being spent in diffusion solvers. And what you can do to handle that, you can actually use parallel. Well, let's see if I could insert, I could parallelize it here. Metadata. So what we could do, we could essentially parallelize diffusion solver by inserting this code. So again, I went to CC3D, ML, metadata, parallel execution, single CPU pod. So since pods is not actually a bottleneck, we could still run pods algorithm on a single CPU and use however many processors we want for diffusion solvers. So that could help with the simulation. I haven't tested it, to be honest, with with this parallel processing. I mean, this is something we could do later. But the original simulation was actually done on a single CPU. And as far as I remember, the early versions of CompuCell, I mean, the ones that we used in 2009, it took, I don't know, a few days to run this whole simulation. I don't know how fast it would be right now, but it's in any way, you have the code, you can play with this. It's not exactly the same code that is that we used to publish the paper, because the CompuCell version is different, but it should be pretty close. And if anything, it's a great starting point for further exploration. So you have pretty complex simulation included in your CompuCell distribution. All right, so let me switch back to, let's see how many steps we went through. Let me pause the simulation for a second. So it's like we went through 40 Monte Carlo steps. I'm not sure this is fast or not fast. Let's switch to this view and let's go to 3D section, 3D view. So this is a tumor. I don't think that any division actually took place. It takes a while before the tumor starts growing. So if you're really patient, you can start running this and wait, I don't know, hour, 2 hours before you see initial results. But it does run. So I think I'll end here, and I'll really turn it to James, who will advance the whole thing to the next. So we'll move to the next speaker, and I don't know who this is.